Okay, welcome everybody. We're happy to have Bob Donnelly, who will tell us about lattice path enumeration for semi-magic squares of size 3.
Okay, so it's great to be back. Thanks to the organizers for the invitation, and thank you to everyone for coming. So today's talk, we have lattice path enumeration of semi-magic squares of size 3. This is the Representation Theory Seminar. This is really going to be a combinatorics talk about representation theory concerns. But we'll definitely, of course, new laptop, so still figuring out the forwarding. Okay, so table of contents, sort of the overview of this is going to be, we're going to start with Pascal's triangle and the up operator. That'll go into Clebsch-Gordan coefficients. That'll go into semi-magic squares. And then that'll come back to Clebsch-Gordan coefficients at the end. The work in this talk, so this is like parts 5 and 6 of a big project. This talk's completely self-contained, but there'll probably be areas which beg to have more said about them, which I won't have time to do it all. So we'll just stick to lattice path counting for this talk. Okay, so let's take a look. Okay, another overview. So to put things in historical context first, Clebsch-Gordan coefficients. Okay, so Clebsch and Gordan did their work in classical invariant theory, specifically with binary forms. And so that leads into Hilbert's work on modules and these things. The theory makes a resurgence with quantum mechanics. Okay, so solving Schrodinger's equation, that brings in spherical harmonics and the atomic model of hydrogen. And we don't want to just study one electron, we want to study many electrons at once. And so the problem becomes coupling of their angular momentum. In the spherical harmonics picture, we're just multiplying special functions together and getting linear combinations of those same special functions. So this would be like, the most basic problem would be multiplying 2 trig functions and you get back another trig function, but with different parameters. Because the situation's special enough, there's a group symmetry controlling everything, and then this can be turned into a tensor product problem for SU2 or SL2C, depending on how you want to look at things. Now, concerns, because there's quantum physics here. Okay, so when we're doing quantum physics, quantum mechanics, we're interested in probabilities. So there is a desire to always bring things back to unit vectors, which introduces normalizations. Another feature, eventually hypergeometric series come into the theory as a major tool. And I'll say this at one point later on, hypergeometric series of type, I guess 3F2. And so that winds up being like a primary method in the theory, in more recent times especially, for studying Clebsch-Gordan problems, modern. I mean, one thing, computation's a big thing. When you do simulations with nuclear physics or nuclear chemistry, you can compute thousands of these things with very large parameters. So it's still very active area of interest in how to compute these efficiently. And so typically the focus is on single sums, and you can get things like asymptotics and the like out of that. And then also semi-magic. So this is kind of the weirdest feature to me, is this appearance of semi-magic squares as a means of symmetries in the problem, which just seems to come like out of thin air. But so that's one thing I want to try to reconcile a little bit with this talk, probably not satisfactorily, but we could fit some of the pieces together to make it a little bit more coherent. Now, so the approach, well, you'll see the formulas for all these things later on, but we don't need unit vectors if we want to do combinatorics. So there's a process where we can denormalize everything, all these square roots go away, and then everything turns into, well, rational numbers or integers or just binomial coefficients and different configurations. Things I won't do today that are definitely of interest, we'll see a little bit of, so the idea, the Clebsch-Gordan coefficients, I just don't want to study single Clebsch-Gordan coefficients, I want to put them in groups. Typically, they'll nicely aggregate in hexagons, and they'll be related by finite differences. And so we'll see that for a little bit, but there's talks I've done before where I spend the whole talk talking about that. And note Pascal's triangle. Part of this project has always gone back to Pascal's triangle to see what's going on there and see if we could bring it into what we're doing now. And that's definitely a motivation for today's talk. Clebsch-Gordan coefficients, they're going to be associated to an elementary generating function. It's not an easy generating function, but it is built out of elementary parts. I'll note that, and again, it's not going to be like a feature of this talk where we could start generating recursions and other good things out of the generating function, but we'll definitely note it. Hockey stick rules, another feature of Pascal's triangle, which we won't do, and they're fun. And finally, in the list of things I'm not going to do today, we also have Vandermonde convolution. I have a feeling that this is sort of kind of like a tip of the iceberg on maybe something bigger. And so this could be advertising for the combinatorics seminar in February. So that's another talk I've got ready. So things always come back to Pascal's triangle, it seems like. So that's where we're going to start today. Okay, so that's big overview, which I won't say much about any of this stuff for the rest of the talk. Now, Pascal's triangle. Okay, so there's a lot of ways to think of Pascal's triangle. Of course, we have binomial coefficients. Here, I'm drawing this differently than I would for, say, an undergrad class. We're going to have it upside down, where the vertex is the minimum entry. What do I want to say about this? And of course, the entries are binomial coefficients. We want to do lattice path counting. So there's two ways to think of that. You could either note, if I want to count the number of paths to any node here, well, I've got to go left and up a certain amount of spaces, right and up a certain amount of spaces, and then the number of left and right always have to be the same to get to that given node, but we can rearrange the order to get different paths, and then that's binomial coefficient. Another way to do this is inductively. What I could do instead is note at the vertex, the number of ways to get from the vertex to itself is just one. And then I can move upwards using Pascal's identity or Pascal's recurrence. And so, for instance, if I want to get to the 10, well, I know to get to the 10, we got to go through the node for the 4 and the node for the 6. If I want to count all paths going to the 10, we just look below and add those numbers together. Okay, and so this is going to be the motivation for what we call an up operator or order raising operator. And so we want to take this process and mechanize it, and we'll just look at it in the case of rectangular grids, although it applies to a lot of other things. Okay, so just to get out the basic definitions, we're interested in partially ordered sets. And so here we'll use P for our partially ordered set. Our relation will be given by less than or equals. We have our three usual relations. And in particular, I'm interested in finite graded posets with a minimum and a maximum. So here, what the graded means, I mean, in the pic, we'll look at the picture of Hasse diagrams. It just means your elements are in nice levels and there are links from one level to the next. You can't jump a level. Formally, we want that the length of every path from the minimum to the maximum is the same number n. And then that guarantees that the length from the minimum to any point is well defined. It doesn't matter what path you use, they'll all have the same length. And then that's what we call the rank of the element. And so we have a rank function. We can collect all the elements of the same rank together. We'll call that the level. And I don't know if I really need this, but we could have the rank number, which is the number of elements in a given level. So this is going to be the main item of interest, even when we go to semi-magic squares. So, for example, rectangular grid. Okay, so we have the Hasse diagram, which is the picture of the poset. All the information of the poset's encoded here visually. Our minimum is A. For instance, the rank of the element H is 3 because any path from A to H is going to have length 3. The level of rank 3 has H, I, and J in it, and the number of elements for that rank is 3. okay, just for an example. And rectangular grids are going to be the driving example for the whole talk. Now, the up operator, what we want to do with this is I want to linearize things so we can do linear algebra, because what are we doing? We're just formally adding things together as we lattice path count. So for our poset, we want to attach a vector space to it, just given by taking formal linear combinations of the poset elements. So that'll give us a vector space. And then if I want to define the up operator, I want the notion of covering in the poset, which just says, okay, you have your formal definition, but this just says, if we look at the Hasse diagram for the element X, Y covers that if it's directly above X with a link. Then I have my up operator, or order raising operator, or order matching operator. What we do here, I just define it on the basis. And the idea is for X, the up operator on X is just going to be to take the formal sum of all elements directly above X. Also, if we're at the maximum, we'll just say that goes off to 0 since there's no place to go. We'll note for elements that are linear combinations of basis vectors all the same rank, it'll just carry rank T to rank T plus 1. So we're just moving up rank wise. And we can reinterpret, if I think of the image, so if Y is in the rank above, the coefficient of Y after we apply this to some linear combination will just be to add the values that are below. So exactly like what Pascal's identity is doing. So just to do it formally, okay, I have a section of the rectangular grid. I'm focused on rank 2 going to rank 3. And we'll just call these X1, X2, X3, X4, X5, and X6. We extend linearly. So X1, X4 is directly above it. Above X2 is X4 and X5, and above X3 is X5 and X6. And when you put it together, you get exactly what we're promising it does. So that's just doing it with linear algebra. Now, we're interested in Clebsch-Gordan coefficients coming from the rectangular grid, but you can back up to more famous combinatorial sequences if you play around with the shape of the poset. So for instance, if I do the zigzag or the serpentine, we'll get the Fibonacci numbers up the middle. And then probably more significant, if I shouldn't put a judgment on that, but definitely an active area of interest and traditionally active is if we take a right triangle off the vertical, we'll generate Catalan numbers. And so that's Catalan numbers. Of course, this is one of the many, and when I say many, of the over 200 interpretations of what Catalan numbers do. Okay, so that's those are some fun posets to play around with. Now, going back to the M by N grid. So here's a little bit of abstract nonsense, which is just to kind of skirt the representation theory to keep things combinatorial, but we still need linear algebra too. Since I'm dealing with a finite poset, U's got to be nilpotent. Eventually, we're going to run out of room. We're going to hit the maximum and go up. The specific number for an M by N grid will be M plus N plus 1. This means we have eigenvalue 0 is the only eigenvalue. And that means maybe I don't diagonalize, but we can look at the Jordan form. So for the Jordan form, the things we're interested in is the number of blocks and the size of the blocks. Right. Note, because the eigenvalue is 0, that means if I want to know the number of blocks, I just look at the kernel of the U itself. And then the dimension of that gives a block, gives an eigenvector basis 1 for each block. We could tighten things up a little bit because with Jordan blocks, you have to go look for your cyclic vector. But here I can introduce another operator, which on elements, linear combinations associated to rank T, is just going to essentially multiply by the rank, although in this form. And then that, for representation theory, that's just turning rank into weights. Now, if we diagonalize H on the kernel of U, we'll notice we get a pattern for the eigenvalues. going from m plus n to absolute value m minus n with negatives. And these are going to correspond to the lowest weights for lowest weight vectors. Finally, note this counts the number of blocks also. If we want SL2R representations, I'm going to want a down operator, which takes from rank T to rank T minus 1. And the down operator is not natural like the up operator is. The up operator just says take the two below and add. The down operator, to get the Lie algebra to come out right, has to have weights on it. And so we won't put that down here. We're really not going to need it. So we'll just leave it there. And really all I need is the Jordan decomposition, but there's an SL2R action here, definitely. Now, for a picture, and I'll go to the next slide and then come back to this one. If we take the 2x3 grid, okay, there's going to be 3 Jordan blocks. So each picture represents a Jordan block. Let me tell you how you get the vectors, which is on the next slide, but then we'll come back. So for the middle block, what's going on here? Well, the ranks are supposed to represent coordinate vectors. And for instance, if I look at the -4, 1, 2, the way I read this, well, the way you should index Pascal's triangle, okay, the way I wrote it down in the first slide was by putting in the path counts or the binomial coefficients, but the actual elements are going to be given by weak compositions, meaning they have 2 parts, the numbers add up to your rank, and we include 0 as a possibility. And so, for instance, these are just directions for getting around the grid from the vertex. So the 2, 1, what do? We go 2 to the left, right 1. That gets the -4. For the 1, we go to the left 1 and then right 2, getting the 1. And then for the 2, we just go to the right by 3 and we land on the 2. So each rank is going to represent a vector. And so here we have a 4-dimensional space. Note over on the right, these are the H eigenvalues. So each rank will have its own eigenvalue. And then I'll also note this top vector is in the kernel of U, because if we apply the up operator, I look above, we add, we get 0. And so that's doing what it's supposed to. Note a little bit annoying, or not annoying, but because I like what Stanley has in his algebraic combinatorics book, the picture is sort of upside down for representation theorists, in that this is the lowest weight vector and the up operator is a lowering operator, but we'll take what we get. Also note the -3 and 2, had I given you the down operator will annihilate this vector here as a highest weight vector. Now, we go back to this picture. And so this is the Jordan decomposition. Each rank is going to give us a vector. And so you note if we do lattice path counting, this grid here, from the lattice path counts, we only get 6 dimensions. For the 2x3 grid, there are 12 nodes, so there's 12 dimensions, and these other parts are going to pick up those extra dimensions, of course, because we're doing a Jordan decomposition. So that fills everything out. You could note on this one, we have the highest weight or lowest weight property still. If we apply the U operator, that'll go to 0. The pattern is just what we get from representation theory for weight diagrams, although here they look like chains, but they're not really chains for combinatorics, since these are vector spaces. Right. Okay, and so that's a picture of, and the most important thing here, the punchline is, all of these numbers here are what I'm going to call unnormalized Clebsch-Gordan coefficients. And so we've been calculating Clebsch-Gordan coefficients by doing this up operator operation on rectangular grids. And I'll tie this to proper rep theory in a little bit. So the thing to note is, well, what's great about this is, I mean, if you did normalize correctly, you could wind up with rational numbers, but there's no reason for it to be rational numbers either, unless you're coming from the combinatorial direction. Of course, these things are, you're going to be doing work over the rationals, so you can always make things integers. Okay. Now, the Clebsch-Gordan coefficients, it turns out we can catch all of those with a single formula, which is kind of amazing. let's talk about the parameters. How do I get control over those three grids that we have at once? First, we start with a rectangular grid. So there's two parameters coming from its dimensions, M and N. In the Jordan decomposition, we'll have that list of weights. Here I've taken the minus out, but we'll get one of these for each Jordan block that shows up. And so that's going to be a third variable. And then we have the weak compositions for once we decide which Jordan block we're in. How do you get to your points in there? That's with the I and the J. And then you can assemble all this to get a single formula. Okay, note, capturing all this in a capital M is supposed to suggest that we're really just doing a matrices here, which we'll see in a bit. So this looks unwieldy, but it's actually pretty good considering the number of variables in it. You're taking an alternating sum, you've got 3 binomial coefficients, but you can still do a lot with this. I'll also note the generating function for this is actually really tractable also. So here what we'll have, it's a bivariate generating function. We have a binomial series, another binomial series in a different variable, and then we're joining things with this binomial theorem term. Okay, and note the binomial theorem term is great because that's actually when you multiply by x plus y, that's just the up operator. And also sort of when I look at this, I could see that there's a joining of things, which is what your tensor product does. So, and again, this you could say a whole lot more about because of course we could start pulling off recursions and other interesting facts about Clebsch-Gordan coefficients with this, but that's in different parts of the project. So here we just want to stick to lattice path counting.
I have a question. I have a question
Sure.
about the generating function. Is the generating function counting something or is it just representing? So what X count and what Y counts?
Right.
Or just representing the summation?
It's representing, so for me, I see it as just that there's a direct line to the summation there.
Oh, okay, I see, I see.
Yeah.
Thank you.
So actually, that's a good question because if we go back to this, I know this is lattice path counting, but combinatorially, I'm not sure what these numbers represent. So that's sort of, you know, when we get to the end, I'll say like, we've got connections, but some of them I just don't understand. So that's one of the big outstanding questions still.
Okay, thank you.
Yeah, thanks. Okay, so a little bit more history. These finite graded posets with SL2R actions, there's a history of this going back to the 60s and 70s with the study of the Sperner property. And so Stanley and Proctor, they reformulate this theory. And in the way they reformulate, the punchline that they get is this thing called a Peck poset. If we have time at the end, please remind me about Peck posets because there's like a little bit of a cultural story there because Peck is not a person. But their punchline is that they characterize things with the Sperner property and their conditions as posets with SL2R actions. And this is still an active area of research. Something of course of interest to me is that one of the people working on it now is a student at Proctor named Robert G. Donnelly. This is not me. And the current state of the research program here is that they're studying other types of Lie algebras acting on posets. And so this is kind of advanced from the 80s. Now, for rectangular grids, we really don't need Peck posets because rectangular grids automatically have an SL2R action behind them. If I take a tensor product of two irreducible representations of SL2R, the weight diagram, you're taking a chain with another chain, and that just turns into a rectangular grid. So you don't have to, there's no mystery of where the SL2R action comes from. That's the natural SL2R action on each piece joined together. And so this would be, so this is how I thought about this problem, say 5 years ago when I was starting out. That's representation theory. I think this picture with rectangular grids is so much nicer though. Now, coming back to the formula, a few more notes. So we have our formula again. When I first got into this, the first place I looked, so sort of the go-to place for Clebsch-Gordan coefficients for representation theory is, so for mathematicians, not physicists, will be Vilenkin's Special Functions book from 1968. You crack that open and the formula for coefficients is really untidy. It's a huge mess. It's this triple sum, it's the alternating sum. They're factorials, uncollected. You've got a giant square root in front of things. Like the first thing you think when you see this is somebody's got to clean that up. But that's because of the unit vector demands for probability. You have to keep the normalizations if you want to do quantum physics, or you want to work with orthonormal bases. The original formulas go back to Wigner, so that's 1930s, and there are a lot of alternate versions of this formula, which when we talk about the symmetries, each symmetry can change the formula up to give you an equivalent formula. So that's noting some more history. And then the last note before we get to semi-magic squares is that we've got our 5 variables, and 5 variables are exactly enough to give you a semi-magic square. So if you assemble these correctly, semi-magic squares suddenly appear in the picture. That's 1950s. So let's change topics to look at semi-magic squares to see what things we can kind of take from there to bring back to Clebsch-Gordan coefficients. So we start from scratch again. I'm only going to be concerned with 3x3 semi-magic squares. So I'll probably forget to keep talking about the size. So you can always assume I'm looking for size 3. Beyond size 3, of course, is very interesting, but also very difficult. I'll call a square matrix a semi-magic square if it has non-negative integer entries. And if we take sums along any row or column, we get the same number, which we call the line sum. Note here, these are not traditional magic squares, so we're not restricted to, say, in this case, it would be 1 through 9. We could reuse numbers just as long as we get things adding up in the same rows and columns. And we don't really, we're not concerned with what's happening on the diagonals either. And so for an example, where I'm flaunting all these rules from traditional semi-magic squares, we get line sum down the rows and columns here, but along the diagonal, I'm going to get a 10 and an 8. So definitely not a proper magic square. There's a lot of algebraic structure with these. And again, I'll have to restrict just for the concerns of this talk. There's a monoid or even a semi-group structure here, and we'll call the collection of all 3x3s just M3. Now, for examples, of course, if I take the 0 matrix, that's semi-magic with line sum 0. If we go to line sum 1, we note immediately we have to have exactly 1, 1 in each row and column, which means we're looking at permutation matrices. So there's 6 of these, and I'll note I'll put the rotations before the reflections when I order these. Not so important to remember the exact matrices, but for things I'm going to do later, we'll want to switch between these two groups. In general, if I want to build semi-magic matrix squares out of old semi-magic squares, the algebra works exactly like you would hope. If you add 2 semi-magic squares, you get a new semi-magic square. The new line sum is the sum of the old line sums. If we multiply by a scalar, so a non-negative integer, same idea. We get another semi-magic square with the expected line sum. So that means we could take linear combinations. And since permutation matrices have line sum 1, we could hope linear combinations of permutation matrices are enough. And then it turns out from Birkhoff von Neumann, going back to the 40s and 50s, I think, they show a bunch of things, but one of the consequences is that every semi-magic square for any size can be written as a sum of permutation matrices as noted. And so that means we have a spanning set given by the permutation matrices. One little drawback, and maybe it's hoping for too much, the permutation matrices won't be linearly independent. So if we go and look immediately for a dependence relation in the 3x3 case, we note there's only one thing that's going to come out when you solve, which is if you take the sum of the rotations, that's equal to the sum of the reflections, which is equal to the semi-magic square of all ones. And so that, if I want to get into counting things, this is the only thing I need for overcounting. So now this might seem a little artificial because I'm only going to work with 6 tuples. And remember, the first 3 are the rotations, the last 3 are the reflections. I want to stack these because that's going to suggest something about the symmetries. It's also suggestive for how you could try to generalize this whole entire picture, which we could say some more about at the end. So I'm going to stack things like this. So rotations up top, reflections along the bottom. Our single relation is going to take the form, if I have 3 ones up top, I could just translate all 3 to the bottom. So we can do this interchange here. If I'm representing a semi-magic square by a rectangle like this, if I want a unique representative, I'll make the choice that we just keep upshifting ones until a 0 appears. And then that will be a unique representation. Okay, we note, of course, the sum of all the A's is the line sum. So moving 3 ones to the top won't have any effect on the line sum. Now, let's do a little warm up with that picture for the rectangles. So one of the oldest results on semi-magic squares, especially of size 3, it's probably the theory starts with McMahon and his famous books. This is not the formula that he had, but and he uses different methods, but this formula goes well with this picture I'm trying to push with rectangles. So the idea is going to be, if I want a semi-magic square with line sum L, we're trying to take a sum of L permutation matrices, which means I'm trying to put L balls in 6 boxes. And so for that kind of counting, which I'll just list at the bottom, the way we do that is we throw away 1 box and then use that for the parameters as so. Now that's going to be an overcount because we've got these semi-magic squares which can have all one, that are missing the zeros. So if I want to throw away the ones that are missing the zeros, we can fix that by just assigning 3 ones to the bottom entries, and then you put whatever you want in everything else. Here we're using up 3 ones, which means I'm only going to have L minus 3 ones available for the rest. And so that's what we're going to discard here is L minus 3 going into our 6 spaces. And that's a formula. And again, this formula, there's a lot more you can say. Like there are variants on the formula. We could talk about the generating function, a lot of fun things that go with this. So that's just a warm up. I'll note for 3x3 semi-magic squares, there are symmetries in here. Okay, physicists certainly know about these. If you have a semi-magic square, you can permute the rows, you can permute the columns, and you can transpose without ruining the semi-magic square property. And so that group, when you take a look at what's going on, is going to give you a wreath product of an S3 and a Z2. It's going to have 72 elements. The way you think about this in rectangle form, that means you can interchange the rows. Okay, technically you can't do column switches. The permutation, well, it's like column switches are not enough. What will allow in each row is you can permute along rows without worrying about what's underneath or above. And so for instance, orbits of 1, 2, 3, 4, 5, 6 would look like this, where I can permute above, I can switch the rows, or we can switch and permute at will. And then that's how the group action looks on triangles. Okay, note, it's not nice in that the transpose does the switch, the transpose won't do the switch with the basis that I've chosen, but something will. Now, M3, semi-magic squares of size 3 are also going to form a graded poset, which all that set up from before was also set up rectangles, but also to set this up. Here, the relation is just going to be checking entry-wise. So for instance, on the bottom, if you know it, you check entry-wise, every entry here is less than its corresponding element on the right. And for the covering relation, we'll say that N covers M if N is just gotten to from M by adding a permutation matrix. And so that tells us everything we need to know about the Poset. Of course, I want to draw Hasse diagrams, but with semi-magic squares, there's so many of them, this will get difficult fast. If I do, so a way to make this tractable, or at least to get things that you can start looking at, because you don't want to look at the full Poset. And of course, we want finite Posets too. If I cut the entries off at 1, then maximum 1 gives us this set of 14 matrices here. Let's see. So the things to note are just the ranks are given by line sum. So we've got 0, 1, 2, and 3. And also the covering relations, you can see that each set of 1s fits inside the set of 1s above. So that holds up too. I'm going to change this up with rectangles. And then we'll also apply the up operator here. And so the up operator, I'll put the lattice path counts as the subscript on the right. And so you notice with your up operator, there's homogeneity behind all this. So we're not going to get a lot of variation. Rank 1, everyone's got 1 path. Rank 2, everyone's got 2 paths coming in. And then at the top, we've got 12. And so that one, pretty easy to get under control. Also a model for what we might try to do in the big picture. Like I said, it gets ugly fast if you're trying to get actual pictures. If I go to maximum 2, we'll have far too many individual rectangles, but what I can do is use the group action to tie everything up into orbits. When I tie everything up into orbits, okay, it's tractable, but also to get a decent picture, I got to change things up. So here for the Hasse diagram, I'm going to put things on their side. The ranks are along the bottom. Those are the line sums also. And for the orbits, you'll note the way we distinguish among the different orbits is by counting the number of 0s, 1s, and 2s. So if we apply the group, those numbers are not going to change. And then there are fun things you can do with this with Vandermonde convolution, which are in the preprint, but that's a big diversion, which we can't do here. Again, I'll switch the rectangles. And so we see here how the rectangles come together. I'll have 2 subscripts now. One will be for the number of elements in the orbit. The second number will be the lattice path count. And note, you could do the up operator here, but it's a little bit delicate in that you can't just do the up in this Poset here. You got to kind of figure out what the links are in the semi-magic square Poset, not the orbit Poset. But if you do that and you got some time, for this one, we know to get to the matrix of all 2s, okay, that's what this one here is at the maximum, there'll be 900 paths. If we go to all 3s, you'll get about 94,000 paths. If we do all 4s, we'll get 12 million paths about. And of course, we go to the OEIS to see what's going on here, and we get a hit. For these actual numbers, there's not much going on in the actual sequence here, but if we take a factor out, what we do, you'll note this is a very small number for the OEIS. We recover the Fresnel numbers, and these are, so Fresnel, this is going back to the 1890s, and he's got 2 books. I'm not up on what he was doing then, but I do know this is in the OEIS at least for like, okay, that's something where we can see what ideas can come out of there for later. So that's always nice to have a talk where you can get the OEIS involved. Now, the question is though, do we have a formula in general? And the answer is yes. So what we'll do, we think about what's going on. I want to put, well, so we've got semi-magic squares. If we think about each permutation matrix as being a direction, what are we doing? We're figuring out the sum of permutations that go to our specific semi-magic square. The order that I sum them in doesn't matter though. And so we can think of that summing process as giving us a word or a lattice path in the different p's that we use to get our square. So for instance, for 2j, all I need is either, you need a 1, 2, 3, 1, 2, 3, a 1, 2, 3, 4, 5, 6, or 4, 5, 6, 4, 5, 6. You need 3 different types of sums to consider there. And so the idea is going to be, in general, what you would do. Okay, the contribution from the unique elements, say, would be just this multinomial coefficient with 6 parts. But I can't consider just that because we'll get contributions also from all the other representatives. We've enumerated those, though, by just counting all the ways we can downshift from the unique representative. And so that's going to give us a sum. And so this is our formula for lattice path counting in the space of semi-magic squares of size 3. If we try out the numbers from before, so using the up operator, I can get to 12. Up operator again, you can get the 900. Probably you don't want to use the up operator for 3J. The formula gives you the 94,000, 12 million the same way. How are we doing? Perfect. Before I go to the next page, let's note there's obvious invariance going on here. If we had gone into like the group action will preserve the poset, so we can get invariance on lattice path counting that way. But also we could just check directly in the formula. If you permute 1 through 3, not going to change the formula. 4 through 6, not going to change the formula. If you do the interchange of 1, 2, 3, and 4, 5, 6, not going to change the formula, but it's going to do a change of variable, which will be important for what's coming up. So this is got group invariance. Now, another thing we could do with the formula is to try to true it up to hypergeometric series. So you would have to bring a factor out so that the first term is a 1. And it's going to turn out that we're going to get a 3F2 for the factor that's left over. Wishful thinking would be, we know it's well known that for Clebsch-Gordan coefficients, they have a factor of 3F2 also, but that doesn't mean the parameters have to line up, but it turns out that they actually do. And so what I can do is, okay, and so this is sort of a combinatorial thing to do, is I can tie up both of these sums, the one for Clebsch-Gordan coefficients and the one for lattice path counting, into a single function by introducing a variable. And I'll just have that where the variable, okay, it's going to be a polynomial in Z where we match the coefficient just to the how far away you are from the unique representation. So we have this, and now with this, I get a result, and this is really just what I said in fancy form, reciprocity, where if I take that function and evaluate it 1, we get lattice path counting. If I evaluate it -1, we get Clebsch-Gordan coefficients, but twisted. And it has to be twisted because the invariance for Clebsch-Gordan coefficients are not going to be as nice as for lattice path counting, but they are invariant. Now, reciprocity with a question mark, because I don't like reciprocity is certainly a well-developed idea in combinatorics, but I don't know how this would fit into it, although this is the shape of it. For lattice path counting, what would this be? What other combinatorial things does lattice path counting count? Well, if I was to take the poset where we just took the maximum to be M, then we would be looking at maximal chains in the induced poset. And if we were to go to the polytope associated with the poset, that would maximal chains would be the same as considering facets. What it means on this side, I don't know. And that's getting back to Rigoberto's question that there's something going on here that needs to be explained, which we're not going to do here. Just a little bit more on reciprocity. Since representation theory, I should at least give an example. And the example I'm going to give, like I said, we're going to go right back to Pascal's triangle with binomial coefficients. And this is like the classic example when you like open books on this stuff. So what do? I'm going to have a function. I'm going to have binomial coefficients, and we'll have n, so that n's bigger than k, so this makes sense. I can expand this out into factorials. Then I'm going to cancel out, and you'll notice we have a polynomial in n. Like the k, I'm not worried about, that's some fixed constant. So this counts, this is a counting function, important counting function. We're going to choose k objects from n. If I replace the n with a -n, I could put it back into our in the polynomial form here. When we clean things up, we're going to get the counting function from before where we put k balls into n boxes. Note, this is a shift of the original function, so that's a uniform shift. And there's also a change in sign depending on the k. So this is sort of the shape of reciprocity in general. And again, it's not only is it a big subject, but I'm also not the person to do it justice. But for semi-magic squares, I highly recommend Stanley's slides from 2014. So these are on his website, and the name of the talk's Dura.pdf. And then in here, there's a lot of numerology of semi-magic squares, sort of explains why they're hard to work with, and then also looks at variations on that theme. So that highly recommend if this stuff's interesting. And then of course, Stanley's green book, he spends a lot of probably the first half of the book on semi-magic squares, also from the point of view of ring theory. Now to finish, so what we've just established is there is a connection between, for some reason, there's a connection of the symmetries on semi-magic squares with the symmetries of Clebsch-Gordan coefficients, or with this thing we're doing with the operator on rectangular grids. So like I said, for me, going back and reading what Regge did, it just seems to come out of thin air, although there are clues certainly from doing tensor products that indicate these operations on a semi-magic square. What Regge does, or what's in the air at the time anyway, is that they take Clebsch-Gordan coefficients with a normalization. You can normalize it again, and then what happens is that these symmetries on the parameters only act by a plus or minus one. So there's no genuine scaling factors or weird breaking up of the sum and doing other things. It's just you multiply by a scalar. If you've normalized correctly, it's just a plus or minus one. Of course, going to this combinatorial picture that I'm trying to push, we'll have genuine scalars coming out rather than just plus minus one. And then that's something that you want to make sure you can compute readily. And so that's the last thing we're going to do in here is just to give you an idea how you use the symmetries of the semi-magic squares to get symmetries of Clebsch-Gordan coefficients. So for instance, there's a big advantage also into using this A notation for permutation matrices. It's very easy to track what you're doing as opposed to the MNK stuff when you're working with semi-magic squares. So if I switch columns 1 and 2, okay, now that's a lot to look at, but if you know it, you're fixing column 3, so you could guess, well, why don't we switch 2, 4, 3, 6, and 1, 5? And that's exactly what's going to be the switch for columns 1 and 2. If we apply that to our unique representative for our semi-magic square, which I need to compute in F, I'll get a new 6 tuple. But then I note if I want to put it in F, F is only defined for the unique representative if you want the summation to come out right. And so we know what'll happen here is, looking at the actual formula for F, it's just going to do a sign change based on the distance from your unique representative. When I go to the theorem, the reciprocity theorem, I can switch over to Clebsch-Gordan coefficients. The terms out in front, which are very large, fortunately cancel out. And then when you clean up the rest, what happens is we'll get this formula in the vector, in the tensor product notation. So when you unpack this, the different parts, what's happening in the tensor product, we're just switching the order of the tensor product. In the picture from combinatorics, we're just flipping the rectangular grid through the vertical. The K, that's the Jordan block that you're in, is going to stay the same. And you'll also note the IJ and the JI switch, and that's great because if I'm flipping through the vertical for the weak composition, I would just want to go to the same weak composition when you do the flip, and that comes out like that. And so we see all we're doing here is a sign change. And as you get into this a little bit more and look at other examples, you'll need the genuine scalars to come out to work with these. So that's the talk. And also bibliography, just the, so there, of course, you can look at the bibliography in the preprint, but the big things in the talk that I'm kind of pulling from. Of course, McMahon, this is his landmark work. Stanley, EC1, semi-magic squares. He does a lot of development in there, basic development. Also reciprocity, you could see kind of the classical version of it there. Note semi-magic squares, to go very deep into them, you can look at his green book, Combinatorics and Commutative Algebra. And then I'm really kind of taking inspiration from the Algebraic Combinatorics book by Stanley. He doesn't do Peck Posets in there, but he sets you up for Peck Posets. He all but says them by name. Certainly that's where the up operator comes from for me. And then also this business with the rectangles and wreath products, that's coming out of there also. And then I'm just taking completely out of context from what he's using it for, but it works. So thanks.
Let's thank Bob for that nice talk.